A very delightful morning to one and all who have joined us through this online platform for the national webinar on applications of mathematics hosted by Department of Mathematics, Government Science College, Autonomous, Hassan. Well, first to begin with the preliminaries, I'm going to take you through the course of things today. First, we'll have the first session, which will run between 11 and 12. And this session will be having a discourse on the application of mathematics in space science by Dr. Xavier James Raj, retired scientist, ISRO, and he's currently the president of Annai Velankanni College, Tholayavattam, Tamil Nadu. The second session will be between 12 and 1 by Dr. Chandrashekhar BM, assistant professor from Dr. G. Shankar Government Women's First Grade College and PG Studies Center, Ajjarkad, Udupi, who will render his talk on LUB properties and its applications. We shall have lunch break at 1 and we'll resume our post-lunch session by 1:30. And our third session will begin exactly at 1:30 by Dr. A. Satyanarayana Reddy, Associate Professor from Department of Mathematics, Shiv Nadar Institute of Eminence, Uttar Pradesh. With his session, we'll begin the third one, and he shall deliver a lecture on pi and primes. And there are a few instructions which we would like to share with our participants today. I'm sure that after listening to this enriching lectures, all of you will have many queries and doubts which you'll have to put across. So please do post them in the chat box. And also remember that not all questions may be taken in because it depends on the availability of the time. And only 100 members can access the Zoom platform, and others can avail this webinar on YouTube as this is being live streamed. And last but not the least instruction is that every participant have to submit feedback at the end of all the 3 sessions. And this is mandatory for the generation of your e-certificates, which shall be issued within 3 to 4 days. And now with these, we should now focus on the commencement of this webinar. They say that mathematics is a music of reasoning. And in our college, the Department of Mathematics has kept this very alive for the harmony, rhythm, and elegance of this music. It keeps its department very vibrant with activities. And this webinar is again a proof for the same, which intends mainly to develop flair among the students' community towards mathematics. And this is also the day in which this Pi Day is being commemorated by the department, which is an annual celebration of mathematical sign pi. Celebration of this day was founded in 1988 by physicist Larry Shaw. And on March 14th was the obviously chosen date because the numerical date 3.14 represents the first 3 digits of pi. And it also happens to be Albert Einstein's birthday. Now, I request a very dynamic, diligent, and the brain behind this webinar, Dr. Vinay Kumar, PN, Head of the Department of Mathematics, Government Science College, Autonomous, Hassan, and the patron of this webinar to convey welcome address.
Thank you, Madhushri Madam. Sometimes challenges and struggles are exactly what we need in our life. May you welcome every effort, every struggle, and every challenge. May you open your wings and fly. Good morning, ladies and gentlemen. Myself, Dr. Vinay Kumar PN, Associate Professor of Mathematics, Government Science College, Hassan. It's my pleasure to welcome you all for today's national webinar on applications of mathematics. Sunshine is a welcome thing. It brings a lot of happiness and brightness. By these words, I would like to welcome our dear principal, Professor Gangegowda SH, President of today's function. A warm welcome to you, sir. Welcome all experiences. You never knew which one is going to turn everything on. Now, it's time to welcome our honorable speakers. First and foremost, let me welcome Dr. M. Xavier James Raj, former scientist, ISRO, and president of Annai Velankanni College, It's my immense pleasure to welcome the speaker of second session, Dr. B.M. Chandrashekhar, Assistant Professor of Mathematics, Dr. G. Shankar, Government Women's First Grade College and PG Study Center, Udupi. Hearty welcome to you, sir. I extend my cordial welcome to Dr. A. Satyanarayana Reddy, Associate Professor of Mathematics, Nadar Institute of Eminence, formerly known as Nadar University, Uttar Pradesh. A warm welcome to you, sir. Each person holds so much power within themselves that needs to be let out. Sometimes they just need a little direction, a little nudge, a little support, a little coaching, and the greatest things can happen. In fact, these words reflects the aim of today's webinar. And I hope this will ignite the young minds who are taking part in this webinar. My delightful welcome to all those participants across the state and outside the state who are taking part in this. Before concluding my welcome address, let me extend my warm welcome to all my teaching and non-teaching staffs as well as students of our college. A flavored welcome to one and all who are taking part in this webinar.
Thank you, sir, for extending a very convivial welcome to one and all. And on behalf of the resource persons, participants, and personally too, I extend a very warm welcome to you, sir. Now, let me request our most respected and unimpeachable principal, Professor S.H. Gangegowda, known for his administrative acumen and a man with insightful perspectives for taking our institution to greater heights. Sir, as the chief patron of this webinar, may you please now address this virtual gathering.
Okay, thanks. A very good morning to one and all. I gladly welcome you all to this national webinar on application of mathematics. Our institution has always stood in the forefront to nurture and broaden the origin of knowledge among its stakeholders. Being the premier autonomous institution to offer higher education in Hassan district, we date back to 1958-59, offering 3-year degree courses, BSc, BCA, and MSc in chemistry. The college has been witnessing incredible growth in its state-of-art infrastructure, advanced teaching methodology, well-established library, eco-friendly campus, and lot of scope for campus selection with tie-ups from coveted industries. All these have made the aspirants of higher education in basic and applied sciences of students in and around Hassan district to prefer our college at a top priority. The college is proud of its legacy of alumni who have made commendable contributions in the field of science and civil services, both in the country and all across the globe. Let me proudly say, Professor Kumar, former chairman of ISRO, is our alumni. Finally, I want to wish you all happy Pi Day and hope this webinar is going to help you in unleashing the unbounded possibilities of mathematics. Our eminent scholar on board today, who will deliver the talks and interact with you, will enhance your aptitude for maths. I congratulate Department of Mathematics for their initiative and wish them all the best and a fruitful webinar to all the participants. Thank you.
Thank you, sir, for your wonderful wishes. Now, I request Shri Jagdish R.D., Assistant Professor of Mathematics, Government Science College, Autonomous Hassan, who is going to be the moderator of our first session. I request him to begin the session with the introduction of the speaker of the first session, that is Dr. M. Xavier James Raj. Sir, over to you.
A very good morning to one and all present here. Myself, Dr. Jagdish from Department of Mathematics, Government Science College, Hassan. I'm very happy to introduce Dr. M. Xavier James Raj, sir. Sir is having a vast experience of working in various organizations. He worked as scientist at ISRO Trivandrum from 1984 to 2018. He had been to Germany and Israel on deputation from ISRO. Sir is having more than 30 publications to his credit and is also guiding many research scholars for their PhD program. Presently, Dr. Xavier James Raj sir is the president of Annai Velankanni College, Tholayavattam, Tamil Nadu. Now, in this session, sir will speak on applications of mathematics in space sciences. Now, let us listen to sir now, and the queries, if any, please put them in the chat box. Sir, over to you, sir. Professor James Raj, sir, over to you, sir, now.
Yes. Okay.
You can start, sir.
Am I audible to all?
Yes, sir. Yes, sir. You are audible.
Okay. Good morning to all. My talk is applications of mathematics in space research. This topic I propose to encourage our younger generation to take interest in mathematics, which are useful in all fields, including space research. So, Roshan, the poor layer. Okay. Okay, my presentations include what is research and what is space research, applications in orbital analytics, application in satellite theories, and if time permits, how we are safeguarding our space missions and IADC predictions. Okay, see, basic important for the research is thinking. Thinking is very important because Apple was falling always, even before Newton. But nobody thought why Apple is falling. Newton thinking produced gravity. So think positively to do a good research. What is research? Research is research is the research is the result of advanced knowledge which was created in the past. It is a systematic process of collecting and analyzing information to increase our understanding and knowledge of the phenomena under study. It is the function of the researcher to contribute to the understanding of the phenomena and to communicate that understanding to others. Research is designed to solve a particular existing problem. So there is a large audience eager to support the research that is likely to profitable or solve problems of immediate constraints. We must understand how research impacts our decision making. Research requires time, energy, efforts, and sometimes money to have the evidence. We need to make a sound decision. That is why many of us avoid it. The research you do and the evidence you gathered will have impact on your future life. In conclusion, research is a very vital tool in our everyday decision making. It arms us from wrong information and save time, energy, and money. The question is, how much information is enough? How much information can we afford? How to do? When you need information, where do we go? Our choice of an information source will influence the kind of information we retrieve. Consider the specific attributes of information and sources before we make our choice. What are the sources available? The book is comprehensive and substantive, but the information may be outdated depending on the date of publication of the book. Machine is popular and focused, but because of a limited amount of space, coverage is limited to only most current information. Journal is scholarly, authoritative, but same problem. Newspaper, it is current, but broad in scope, but it is non-substantive. Worldwide web, internet, it is easily accessible nowadays, broad in scope, but it is unreliable. So how to do research? Doing research, we will look into the books. From the books, we will go to articles in the journal, search in the internet, evaluate all information we gathered, and the result with the citing sources, which give credit to our research. What is meant by space research? Space research or exploration itself is a multidisciplinary subject, and many branches of science contribute significantly towards its development. All basic sciences, including mathematics, physics, chemistry, and statistics, play a major role in space research. Space researchers often come across the situations where scientific answers only be obtained after a detailed mathematical and statistical interpretation of complex data. For that, mathematical modeling and analysis are two main fields with the potential usages in space research. The knowledge and understanding of huge data obtained through major space activities of around a century require a detailed analysis using various mathematical models. Comparison between data and nonlinear mathematical models are also needed. So, application of mathematics starts with orbital mechanics. What is orbital mechanics? Orbital mechanics is concerned with the orbital motion of space vehicles under the influence of gravitation and other external forces. It is founded on the basic principles of celestial mechanics, which is concerned with the natural motion of planets. Fundamental basic ideas are from Newton's law of motion, law of gravity, and Kepler's three laws of planetary motion. We know Newton's law. The important is Newton's law of universal gravitation, which says force equal to sum of masses into gravity divided by distance squared. We know Kepler's law and the coordinate system. Coordinate system is a useful tool to represent any point in space. In practical, several coordinate systems are used in the study of motion of the Earth and other celestial bodies. For the coordinate system, you know, the needed fundamental elements are one origin, a fundamental plane passing to the origin, a reference line from the origin towards some reference point. So this is the Keplerian orbit or orbital elements. Here fundamental plane is Earth equatorial plane, and the center is center of Earth. The reference line is towards first point of values. What are the fundamental elements? It is equivalent to equivalent to position and velocity vector, x, y, z, x dot, y dot, etc. Equivalent orbital parameters is size, that is semi-major axis, and eccentricity. That you know very well, orbit size of the orbit, and then inclination, that is orientation. That is the angle between the orbital plane and the equatorial plane. That is called inclination. And the right ascension of ascending node, capital omega, that is from reference line to the ascending node line. Next one is small omega, argument of perigee, that is ascending node to perigee point. The last one is position of the satellite, that is perigee point to position of the satellite, that is called theta or V or F, whatever maybe. It is called a true anomaly, and it is a past variable. These 6 elements form an orbit which is equal to x, y, z, and x dot, y dot, etc. This is the true anomaly, which is called past variable, because without perturbation, if you know, see, all other elements will be constant, true anomaly will be varying depending upon the time. So, solution of simple two-body problem. That's what I told you. 5 of the 6 elements, except the true anomaly or mean anomaly or eccentric anomaly, we constant for a simple two-body problem. The only parameter to be determined is either true anomaly, eccentric anomaly, or mean anomaly. There is a famous equation, Kepler's equation. Even today, lot of research is going on in this equation solution, and many mathematicians are doing research on the accuracy of the solution of this Kepler equation. So this equation is very important. This equation depends upon either elliptical or parabolic orbit. This sign will change. R is the radial distance, and A is the semi-major axis of the elliptical orbit. You see, ground traces, it is very important to know the path of the satellite in orbit. It is a path traced by the sub-vehicle point at which the normal from the vehicle intersect the surface of the Earth. The formula is lambda and alpha. We will find lambda, alpha, and pi from these equations and generate the ground traces. See, this is simple ground trace, path of the satellite. It is one real satellite ground trace. And visibility. Visibility is important for communication. Without visibility, we can't communicate with the satellite or satellite cannot communicate anything to the world. This visibility depends upon elevation angle. That is, this is observer center coordinate system. That fundamental plane is horizontal. This is, suppose this is the satellite. You draw a perpendicular which come to the horizon. The angle between this horizon to the object is called elevation angle. If this elevation angle is greater than value of the station elevation, that is all tracking station is having a station elevation. It depends upon the station elevation and the elevation of the angle to find the visibility. During visibility time only, we can have the communication with the satellite. So these ground rays and visibilities, everything are generated by mathematicians only, not by anybody else. Now POD, preliminary orbit determination, computation of an orbit from a limited observed data, that is very important. During the visibility time, we will get limited data. With the limited observed data, it is very difficult to compute the orbit. Historically, Gaussian and Laplace methods are very important in the literature. POD is the process of formulating first approximation to the set of fundamental elements that define an orbit. That is nothing but AEI, capital omega, small omega. Here, the effect of all perturbations should be neglected. Only the motion is defined with respect to mutual attractions of the body. That is Earth and the object. And POD is a two-body problem, closed form solution to the equations of motion. From two observations, R1, R2, and the time interval between this R1 time and R2 time, T2 minus C1, determination of orbit satisfying these boundary conditions can be obtained in many number of different techniques. Number one is Gaussian. It was developed in 1801 and the first minor planet, Sirius, was discovered on 1st January 1801. It is observed for 3 weeks and then we were not able to find it. So the problem of determining the orbit from the meager data we got for some weeks was of great difficulty. So after 3 weeks, this minor planet was not observed, but 20-year-old Carl Felix Gauss, a mathematician, entered into the problem and devised a formula which, using that formula, Ceres was rediscovered in the predict position at the end of the year 1801. This is an iterative process through the ratio of sector to triangle. Then Lambert-Euler POD. Euler proposed an analytical method for parabolic orbit. It will work only for parabolic orbits. But Lambert and Euler together developed elliptical and hyperbolic orbits. This is also an iterative process. Then iteration over P we know A into 1 minus E squared. Iteration to true anomaly, F and C series method, iteration on eccentricity is PRS COBOL 1960 board methods of astrodynamics. It is book like Bible or Bhagavad Gita for the space scientists. So this is another method. You see, all these methods, we mathematicians did the comparison. When we need immediate thing, we can't find out which one we can use. So we have done analysis and found accuracy-wise, coverage-wise, convergence-wise, computation time-wise. So final conclusion is, if the true anomaly difference between the two R1 R2 is 70 degrees, then Gaussian method we will use, and we will use iteration, reiteration method if true anomaly is greater than 70 degrees. So this is a contribution of mathematicians, nobody else. So orbit prediction. In orbit prediction, perturbations play an important role. If there is no perturbations, the orbit will be a perfect elliptic or sphere. But due to lot of perturbations, the orbit is not a perfect sphere or perfect elliptic. It will have lot of fluctuations due to the perturbing forces. What are the main perturbing forces? Force field of the primary body. That is, if we consider satellite, primary body is Earth. Earth is not a perfect sphere. It is having mountains where altitude will be more. It is having down, sea and all. So it is not a perfect body. So shape of Earth, atmospheric track differs place to place depending upon the position of the satellite, solar radiation pressure, attraction of other celestial bodies like lunisolar, etc. So the Newtonian equation of motion this is the equation of motion. This very important in the downside, that the denominator R is coming. When denominator R is coming, and if this R is small, for example, the re-entry type, when the vehicle is coming near to Earth, this R will be very small. At that time, doing numerical integration will be very difficult. Lot of numerical errors should come. So our prediction may not be accurate. So people are trying to avoid this singularity and doing lot of research on these equations. So one of the solution for precise orbit computation, which is necessary for mission planning, re-entry prediction, lifetime estimates, and so on. Accurate ephemeris cannot be generated by numerical integration. And also it is so costly, time consuming, and are of questionable validity in kayak across the region due to the non-linearity of the equation of motion. So in the scientific field, a growing interest exists which stabilizes the equation of motion to reduce the combination of local numerical errors or use of other integration subsize or both. One such transformation is known as Kuštanja-Sebel case. These Kuštanja and Sebel both are mathematicians from Russia. They found and regularized the nonlinear equation of motion and reduced it into linear differential equation of motion. These equations are powerful with respect to any type of perturbing forces. These equations are less sensitive to round-off and truncation errors. These equations are everywhere regular in the unperturbed case and all case elements. These case elements are equivalent to orbital elements or constant. The equations are smoothened for eccentric orbit because eccentric anomaly is the independent variable. These equations have been used effectively to generate analytical solution with respect to Earth's obliqueness up to 6th order and air track perturbations. And a number of research papers were published in reputed journals. Also, these equations were used to tackle real problems like IADC re-entry predictions. What is this case transformation? We generalized the Levi-Strauss matrix in 4-vector components. This is the Levi-Strauss matrix. The upper 2x2 matrix is nothing but Levi-Strauss matrix. Using this three-dimensional vector x1, x2, x3 in physical space is transformed into a 4-vector by adding its fourth component as 0. That is x1, x2, x3, 0 is equal to u1, u2, u3, u4. Hence, a similar transformation like Levi-Strauss is redefined as x equal to L of u. This generation of Levi-Strauss transformation is called case transformation, and this case transformation gives a wonderful checking parameter that is called bilinear relation. This relation we can use each integration stepwise. We should get near 0. Applying this case transformation in the nonlinear coupler equation, we obtain 4 second-order linear differential like this. This is nonlinear because in denominator no order is coming. So this is for without perturbation. With the perturbation, this equation of motion will become like this. P is the other perturbations than potential. P is the potential, earth potential. So this is the equation of motion for case variables. This is the equation for potential earth up to 6th order. This is the transformation, how it is coming, and knowing the position and velocity vector at t0, we will compute R, W, Ui, Ui star with these equations, and by adapting eccentric anomaly at 0, we obtain the initial case elements like this. Then it will be formed. After this case elements, people did again research and find case uniform regular canonical equations of motion. It is a particular canonical form of case differential equations. These equations permit uniform formulation. What out may be the motion, whether elliptic, parabolic, or hyperbolic, same formula can be used. These are found to provide accurate, short, as well as long-term orbit prediction numerically with any number of tested harmonic terms. These equations are used to generate analytical solution with respect to J2 to J4. We developed a non-singular analytical theory for the motion of satellites with the air track effect systematically and published various papers in the reputed journal. This is the corresponding canonical form of the equation of motion. H is nothing but Hamiltonian of the system. P is perturbation other than the potential. Hamiltonian system is like this. It is in 3 order. We want 4 order. So we will add a native of the energy, which prescribes the canonical form. So you see, this transformation is very important. This is the beauty of this transformation. That is dt by ds, which is equal to some transformation. This parameter, we found it can be r. When we put r, that is the velocity with respect to the new variables is nothing but r into r dot. R into r during DND time, r will become very less and r dot is huge. Velocity will be more when the body hits the earth. So this new velocity compensates and the new equations work perfectly well. So these are the equations of motion. This is the bilinear relation. So this is the generating function. At last, we will get the equation motion like this. So once Hamiltonian is known, we will be able to find all 9 equations. This is the solution from the orbital elements, that is case elements to case variables. The corresponding elements are calculated from this. So we did a long-term orbit prediction with Earth's flattening. This is the equation with respect to diurnal and terrestrial harmonics. And we use the real satellite data, IRS 1J, and compared for 25 days, not 1 or 2 days. You can see it is observed actual data. Oh, this is with respect to both diurnal and terrestrial. This is with respect to diurnal alone. So, seeing this within 25 days, the difference in important orbital parameter A is 45 meters. When both terrestrial and diurnal terms are considered, and 80 meters only diurnal terms are considered. Eccentricity difference, I difference, capital omega difference, which is a very good comparison, and the case canonical variable is working very well. This is the plot difference. You see the difference. First 25 days, if we see very less. But when time goes, difference will increase. A, E, I, capital omega, small omega, mean anomaly. This is perigee. Perigee itself, you see anything up to 25 days, it is pakka. So this is apogee. This is that bilinear checking each integration subsize. See into 10 power minus 9 is near 0, it is 0. So now short-term orbit prediction. Why we need short-term orbit prediction? The long-term orbit prediction needed for satellites. For short-term orbit prediction needed for vehicle in coasting phase. When the coasting started, till the end of the course. It is a short duration. What is the orbit? What is the size? For that, short-term orbit prediction is needed. This you know. This is time parameter. This is analytical integration. No numerical integration. Because it is needed for onboard computer. So onboard computer, we can't do numerical integration because of time factor. So immediately we have to get it. So this is the Hamiltonian. This is the potential parameter. This is the equation of motion. And this is the analytical integrals we have used. And this is the analytical solution. In computer, you field only these solutions. Use the initial conditions, we will get the solution. Okay. This is very important. This is the actual data. First, the numerical is the actual data. But so many analytical solutions are available in literature. This is case variable. Even case variable, x 1 meter difference is coming. And it is 2 meter difference. Everywhere you can see the difference. But whereas our theory, case canonical elements, it is up to meter level accuracy. It is needed for onboard computer. And if we give fourth order solution, there also we can have a very good accuracy up to meter level accuracy. This is the real satellite data for more than 30 seconds, 30 minutes. This is for full revolution. One orbital period is 645 minutes. XYZ axis difference you can see. It is less than 22 meter only. Air track. The effect of air track on a satellite orbit is quite different from that of gravitational fields. Since the air density decreases rapidly as height above the Earth increases. So satellite, when it is in eccentricity orbit, it is mostly affected by perigee portion. Because perigee will be near Earth, their track will be more. So equations are like this. This is also analytical solution. And these are the equations. How much calculations? Everything is done by mathematicians. This is final equations of motion. Using Bessel function, we have integrated. And analytical solution. This is the analytical solution. This we have used for 1000 revolutions. This 1000 revolution, this is with respect to case variable. This is only difference in semi-major axis, and our case variable difference is very less. It is published in Planetary and Space Science Journal. This is eccentricity, similar trend, inclination, similar trend. This is eccentricity. This is eccentricity variation. 0.02 by 2.2 eccentricity variation. So this is also eccentricity variation. Now eccentricity varies with respect to different eccentricities, different inclination. What is the semi-major difference? You can see everywhere. Case canonical is no error, we can say, very close. This is with respect to inclination change in eccentricity. So this is operate parameter, same procedure you can see everywhere. Our case is error is very important. This is starting from 0. And so it is down. All other solutions are having much error. Due to time, I am hurry up. This is day to night variation because density is having difference between day and night. So what is its effect is found. These are all mathematical formulas, same front. You can see case, this is case, this is net 0. Same front. This is scale gauge variation. Depends upon height, density will change. What is its effect? So what is conclusion? Due to symmetry in the uniformly regular case canonical equations, only 2 equations need to be solved, and the rest of the 7 equations are solved by changing the initial conditions. One can say that in mathematics, we used to go 3 dimension to 2 dimension for simple calculation. But here, we went 3 dimension to 4 dimension. So dimension is increased. Even though dimension is increased, instead of 9 equations, we will manage with the 2 equations. That is the beauty. And the comparison shows that it is working perfectly all right, even for short or long durations. Future work, lot of work is there. If anybody is interested, they can do. These are the publications from this. Then a 2-line element. Yeah, this is very important because in practical, we have to safeguard our space machines. Traffic in space is more challenged than the traffic in Bombay or Delhi. That much space debris are moving in the space. So, our rocket launching, when the rocket is going, other debris should not hit on the rocket. Then our whole launch will be failure. Vehicle will be tilted one side and the launch will be failed. So we have to see collision avoidance. None of the existing debris should hit our launchers. Similarly, our active satellites should not be disturbed by the hitting of other space objects. So for that, we want the data of the debris. That data is given by USA public domain. From the public domain, we will download the existing debris, bigger debris, more than 10 centimeter height. And that data is not in the orbital or Keplerian elements, it is in the form of 2-line element. This is the 2-line element. And from this 2-line, we will download 2-line element. But all our calculations are in the Keplerian orbit, actual orbit we want. So we will convert this CLE into actual orbital elements. This conversion is very important because the generation of CLE depends upon the theory which we have used. These CLEs are mean element and our Keplerian element is oscillating element. What is the difference between mean element and oscillating element? Mean element is constant for over a period. Same, it won't change. Whereas actual elements, it will change time by time. Second by second, it will change due to perturbation. So we will convert the element into Keplerian elements and use it for our calculation. And this is safeguarding our launch vehicles collision avoidance analysis. So collision avoidance analysis will be done for the entire launch window, and all launches it will be done. There are some procedures due to time limit. I am not going that. This will be the graph we generate. Mathematician will generate. This red line, if this red portion is there, we will give not to launch at that time. Because if we launch this time, our vehicle will be hit by the debris. So what we will do is, if this time launch is coming, we will either prepone or postpone the launch to save our launch vehicle. This is for satellite in the orbital phase. So you see, this is number of launches, slips of time changed due to mathematician input collision avoidance. This is 2011, one launch. 16, 2 launches. 15, 1. 18, 3 launches. 19, 20, 21, no delay. In 22, PSLV C53, 2 minutes. These are the changes of time. This is what we project proposed. By doing analysis, we told it to delay this much time to safeguard our launch vehicle and the satellite. So this is the actual lift-off taken. Instead of this time was taken. So what? This is for our satellite. We are having 24 low Earth orbit and 28 geostationary orbit satellites. For all these 52 satellites, we are doing analysis to safeguard these satellites from the debris hitting. So these are the procedure, how to do it. These are the satellites. Okay, the satellites which we are monitoring. So by inputs, set vector, we will get from our S-band antennas, and these TLEs will be taken from this website, and the weather report, weather is very important, we will take it from this. This is the applied mathematician. These are done by mathematicians. This is the data we will give it to a project. This is the threat. If near threat, near 100 meter, any object comes, we will give alert. And we will give what is the delta V needed for maneuver. These are the maneuvers done by this much additional velocity we will give, so that actual orbit will transfer into some other orbit, and if we do it, we will again maneuver it and bring back to the required orbit. When we give this much velocity more, our semi-major will change in 15 minutes, 123 meters, sorry, not minutes, meter, 93 meters, which will safeguard our satellite. These are the number of maneuvers carried out during 2010 to now. 2021, 15 maneuvers. In 2022, 21 maneuvers are done. So year by year, maneuver is increasing. If we see it from 2015, it is increasing trend only due to increase of debris. So these are the things. Another thing is IADC is an Interagency Space Debris Coordinator Committee formed in 1993. As of now, 11 countries are participating, including USA, Russia, France, Canada, Italy, everything. ISRO is also a member. This work is done by mathematicians. And in IADC, every year at least one object they will take part re-entry predictions. This re-entry prediction started from 1998. But India, we participated from fourth re-entry campaign. That is 2002 onwards. So in 2018, our prediction was the best, no error. Indian debris, 2 debris were taken from India in 2019 and 20, in which we were second best. These are the various methods we are using for re-entry prediction. These are one example. See, this is our re-entry prediction in 2015, where our prediction matches 0. Very well, exactly what happened. So this is that prediction. India ISRO prediction is 0. Error is 0. Whereas all others, error is having. So this is that ground truth. It was re-entered in this point. Why these re-entry predictions are needed? Because if it fallen on landmass, lot of damages for property and humans. To avoid this, we have to find the exact location. When we find the exact location, if it is landmass, we will send the people out, or we will try to send this object somewhere else. These are the AADC prediction carried out from 1998. First 4 we have not participated. 4th onwards we participated, but we have not compared because initial stage. After that we were comparing and we were best among all. At least we are not part of a maximum, we will have 5th place. These are 23rd reason. This I don't know position because after my retirement. So high eccentricity orbit. See, this is very important because perigee is less and apogee is very much. Russian all communication satellites are this type of high eccentricity orbits. So these orbits have large variation in velocity due to various perturbation during a revolution. The computation efficiency of numerical methods also decreases. So rapid decrease in perigee altitude decay by combination of lunisolar activities. This is very interesting. If you see, by changing this graph, we will say golden graph. You see, this is the orbital lifetime. When we change a second time, the lifetime of the satellite is increasing, decreasing. There is no constant. So we will fix that all the time depending upon the utility of the satellite. You see, these are the things, few things I explained very quickly, may not be very detailed due to time delay, but if you, this I did it only to take interest on the part of youngsters to study mathematics. We are not becoming any engineers or anybody. Mathematicians are much respected in our field, particularly in ISRO. There is a applied mathematics division where only mathematicians are working. So with this, I think time is too much. I conclude my presentation. Thank you very much for the opportunity. If you are having any questions, you can ask now, or even you can contact me through email. I will be very glad to reply. And actually, I am very glad to hear our former chairman, Kumar, was the student of this institution. Thanks a lot.
Well, we have come to the end of this session. Sir started with space research, and also he introduced many of the applications of mathematics to space research. Let us look into the chat box if there are any questions. I cannot see any questions in the chat box. Sir, from my side, being a basic science college, degree college, who will be studying the undergraduate course in science, can you brief out any of the opportunities in space research for our undergraduate students, sir?
Surely, in the show, BSc Mathematics, Physics, Chemistry people are recruited as scientific assistants. So they will advertise it and conduct the examination. When in the examination it is scrutinized, they will conduct the interview. Almost every year advertisement is coming. You have to see the English newspaper or website of ISRO.
Okay, sir. Yes, sir. Yes, sir. It was really a fruitful session, sir. I think all the listeners and participants have cherished by your talk, sir. I would like to thank you, sir, Dr. Xavier James Raj, sir, on the behalf of the organizers and on my personal behalf, sir. Thank you very much, sir. Thank you.
Thank you. Thank you. Thank you.
Over to Madhushree, ma'am.
Yeah, thank you, sir. Once again, I must just say that a man of his stature, Dr. M. Xavier James Raj, joining us today itself was a very, very proud thing for us in GSC Hassan. And I must say that we are all humbled and, we are so humbled before his knowledge and simplicity. Thank you once again on behalf of the entire family of GSC Autonomous Hassan, sir. Thank you.
Thank you. Thank you.
And now, moving forward, I now request Dr. Vijay S., Associate Professor of Mathematics, GSC Hassan, the moderator of this session, to kindly take forward with the introduction of our resource person, Dr. Chandrashekhar BM.
Good afternoon, one and all. Welcome back to the second session of our webinar. My name is Vijay, Associate Professor of Mathematics, Government Science College, Hassan. I am so pleased to be here with you and to have the chance to introduce our guest speaker, Dr. B.M. Chandrashekhar. He did his MSc Mathematics with the distinction in 2003 from University of Mysore and pursued PhD on the thesis entitled A Study of Some Topics in Theory of Partitions. under the guidance of Professor Padmavatamma from the University of Mysore in 2016. Sir is having more than 15 years of teaching experience, both in engineering and degree colleges. He taught engineering students, graduate and postgraduate students. Before joining government service, he worked as lecturer in Dayanand College of Engineering, Bangalore. Currently, sir is working in Dr. Shankar Government Women's First Grade College and PG Center, Ajjarakadu, Udupi. He worked as BOE in Mangalore University in 2015. He invited as resource person in many colleges. He attended and presented research papers in many conferences and workshops. He published more than 14 research articles in reputed national and international journals. Now, in this session, sir is going to talk to you about LUV properties and its applications. We are all very fortunate to have such a dynamic person with us for this today's session. Let us listen to sir now, and queries, if any, post it in chat box. He will answer your question after his talk. Please, Chandrashekhar sir.
Thank you, Vijay. I'm very happy to be in this national webinar. Thanks to Vinay also, and thanks to Government Science College. And fortunately, in 2001, I completed BSc in Government Science College only. So I'm a old student of Government Science College. So I'm happy to say this. And I'm very happy to give a talk to this college as a lecturer, degree college lecturer. So today my topic is least upper bound property and its applications. This property is the, let me share my screen. Are you able to see it, right? Is it visible?
Yes, sir. Yes, sir.
Okay. So before stating what is LUV property and its applications, I'm a lover of real analysis. This one created by great Professor Kumar. You can see more results regarding this in his textbook, Real Analysis by Kumar sir and Ajit Kumar. And also he has given a lot of video lectures. It is available in YouTube. You can refer for further studies. In real analysis, so we more concentrately on real numbers. So in the beginning, we started with natural numbers, then integers came, then rational numbers, then after that, irrational numbers came, then together this with real numbers. So Dedekind, we all of you know that Dedekind constructed real numbers. So in the earlier days, we started with natural numbers, counting what we see, we are counting that. From natural numbers to broader set, we move to integers. So there is a saying, if you move from one thing to another thing, we get something good thing also, and we also lost some good properties. So natural numbers have very good property, that is well-ordering principle. Well-ordering principle says that so any non-empty subset of natural number has a least number. So it is a very beautiful property that natural numbers have. From natural numbers to integers, we gain that integers is a group. All of you know that with respect to addition, Z is a group. And from integers to rational numbers, we lost the property. From natural numbers to integer, we lost the property well-ordering principle. In integers, there is no smallest element. So that is the property we lost from natural numbers to integers. But we get some property, that is what from in integers with respect to addition, it is a group. And from integers to rational numbers, when we move on to that, we know that the rational numbers are countable. So this is the very beautiful property. And the integers also countable. Rational numbers are also countable, but rational numbers, one more thing from integers, it is a field. Rational numbers are field, but integers are, we know that it is a ring, but it is not a field. And what is the property we lost from integers to rational number is, in given any integer, there is a previous number and next number we know that. That is consecutive integers we can found in integers. But in rational number, if you give any rational number, there is no, we can't say that what is the next rational number and what is the previous rational number. Suppose, let me take 0. 0, all of you know that 0 is a rational number. But when you look at 0 as an integer, we know that -1 is the previous integer and 1 is the next integer of 0. But in rational numbers, so what is the next rational number of 0? We don't know. What is the previous rational number of 0? Also, we can't say exactly. So rational numbers are dense in real numbers. So this is the property we gain, and rational numbers are countable, rational numbers are field. From rational numbers to, when we move to real numbers, the least upper bound property is the most pillar of real analysis. If you remove this property, real analysis will fall down. So main results, most of the main results in real analysis, directly or indirectly, they are using least upper bound properties. We'll say that what is least upper bound property later. Just I am introducing why this LUV property is most important in real analysis. If you remove that LUV property, we get only algebra. That is, we know that the functions are continuous. Adding of two functions is continuous. Just like that, algebra properties we will get. And the most important property, this LUV property, so it is the pillar for real analysis. I'm again saying that. And the rational number does not have this LUV property, and real number having this property. And when you move to from rational number to real numbers, I told you that LUV property is the gaining thing, and the last property is rational numbers are countable, and we know that real numbers are not countable; they are uncountable sets. So these are the properties when you move from one set to another set, and the set becomes larger and larger. So we are getting some new properties, and but also we are losing some good properties. In natural numbers, Velankanni principle, but when it comes to integers, there is no Velankanni principle. And when it comes to integers have group property, but in natural number is not a group property. There is no inverse in natural number with respect to addition. And also there is no additive identity also. All of you will know that. And from integers to rational numbers, we know that it is a field, but integers, it is only a ring. And from rational numbers to, in integers, we have consecutive integers. We can say that what is the, if you give any integer, we can say that what is the previous integer and what is the next integer. So, but when it comes to rational numbers, this is the property we don't have. But rational numbers are field. You know that rational numbers is field. From rational numbers to real numbers, you know that real numbers has LUV property, but rational numbers does not have LUV property. So first, before stating what is LUV property, just look at what is an upper bound and what is least upper bound. Then we'll come to what is least upper bound property. Is there any BSc students? How many BSc students are there? MSc students are there? Vinay or Vijay? I want to know that what are the audience?
There are no PG students in this college, sir.
Okay, all are BSc students only. Okay, then.
Yes, sir. BSc and BCA students.
Okay. So then I have to the abstract things I have to make it much more easier.
But from outside there are many PG students are there.
Okay. Thank you. Okay, first let me define what is an upper bound. Before looking at what the proper definition of upper bound, just take some example. So we are in okay, let me consider in government science college. Consider the height of the student's height. Consider the heights of the student. So here measurement comes. So we say that 5 feet, 4.8, 5.6. So like this, so everyone has their own height. So if you consider these height measurements, what is the what will be the maximum height? Suppose say that 10 feet. 10 feet is also no, everyone in the students group less than 10 feet only. Usually no one will be the longer than 10 feet, right? So 8 feet, if you consider 8 feet also will be the upper bound. That means every student in the government science college will be less than or equal to 8 feet. If you consider 6 feet, 6 feet or 6.5 feet, it will be more precise. So the upper bounds may be many more, but among them, if you consider the among them least, that will be the least upper bound. Let me define precisely. Consider any non-empty subset of R. Consider any non-empty subset of R. Let A be any non-empty subset of R. If you want to say that A is bounded above in R, there is some real number alpha in, let us say that alpha in real number, said that every element in A less than or equal to alpha. So then we say that the set A is bounded above and alpha is called upper bound of the set A. So that means you can see that if you consider any subset of R, and if you consider this real number alpha, every element of the set must lie to the left of this alpha. Every element of A should lie to the left of alpha. Then we say that alpha is an upper bound of A. And any number greater than alpha, that will also become an upper bound of A. For example, let me consider the set A is equal to open interval 0, 1. In this set, there is no maximum element. There is no largest element in open interval 0, 1. We know that open interval 0, 1 means what? All real numbers lies between 0 and 1. Rational numbers will come, irrational numbers will come. There are infinitely many real numbers are sitting in this open interval 0, 1. So if you draw real line, and if this is 0 and this is 1, all these real numbers, there are infinitely many real numbers are there. Here we say that this alpha belongs to R. Alpha need not be an element in A. Alpha is an element in R. So in this set, so we say that 1 is the upper bound of this set. Every element of this set less than or equal to 1. And if you consider 2, that will also become an upper bound. If you consider 3, that will also become an upper bound. 1.1, that will also be an upper bound. So there are infinitely many upper bounds are there. All the elements greater than or equal to 1 are upper bounds of this set. Among this upper bound, one is the least. So 1 is the least upper bound of the set A. I think you are familiar with, are you able to follow what I am saying that? Let me take some more example. Let me consider A is equal to set of all natural numbers. Set of all natural numbers. If you consider natural numbers, there is no real number. Said that every natural number is less than or equal to that real number. So we can't find, there is no real number alpha in R. Said that every n is less than or equal to alpha. Every n is less than or equal to alpha. We'll come later. This is a very good property, Archimedean property. We'll do it later. So some subsets of R has least as upper bound, and some sets don't have upper bounds. And if you consider A is equal to closed interval 0, 1, So here in this closed interval 0, 1, here 0 is also included, 1 is also included. Here upper bound is 1 and 1 also belongs to the set E. So we need to observe that to define an upper bound, the upper bound need not be the element in the set. So it is in real number. So here in some sets it belongs that. When it belongs, then we say that upper bound, the least upper bound and the maximum, they are same. So here 1 is the upper bound, 2 is also upper bound. The all numbers, real numbers greater than or equal to 1 are upper bounds of this set. Let us say that this one is A1. And 1 is also, among all upper bounds, 1 is the least upper. So let us define properly, mathematically, what is the least upper bound. Least upper bound. So we usually write LUB. Consider any, as usual, non-empty subset of R. There is an element, there exists an element alpha in R, is said to be least upper bound of A. The first thing is least upper bound. There are two things. First, it should be upper bound. Among all upper bounds, it should be the least. So there are two things we need to look at it. So when we consider the example, all the height of the students of Government Science College, students' height, if you consider 10 feet, 8 feet, 9 feet, 7 feet, like this, these are all becomes upper bound. But if you consider the tallest student in the class, suppose say that he is 6.5 feet, then he becomes the least upper bound. His height becomes the least upper bound among all the students' height we consider. So first he should be the upper bound. First he should be the taller. Then among the taller person, he should be the least. So here alpha must be an upper bound. Alpha is an upper bound of A. The second thing should be if any element smaller than alpha is not an upper bound. So any element, let us say that if beta is smaller than alpha, then beta is not an upper bound of A. Here we see that what is the upper bound definition means. Alpha is said to be an upper bound. There exists alpha in R. Alpha is said to be an upper bound of the set A. For every x in A, for every x in A, for every x in A, x should be less than or equal to alpha. For every x in A, x less than or equal to alpha. So this is the condition. So for every x in A, x should be less than or equal to. And when do we say that alpha is not an upper bound? So alpha is an upper bound. Geometrically, we can see that every element to the left of this real number, then we say that alpha is the upper bound. Suppose I want to say that alpha is not an upper bound. I want to produce one element x in A such that it should be greater than alpha. That means what? Whatever here we have written, given any alpha in R, I can find a element in A such that x is greater than alpha. So that is what the negation of an upper bound. Let me repeat again. Upper bound means what? Alpha is said to be an upper bound. For every element in the set, x must be less than or equal to alpha. And if you want to say that alpha is not an upper bound, I want to produce at least one element in the set which is greater than alpha. So in this set, 1 is an upper bound, and all 1 by 2 belongs to A, and which is smaller than 1. And if you want to say that 1 by 2 is not an upper bound, I want to produce one element here so that 1 by 2 is not an upper bound. So can you give any element which is greater than 1 by 2 here? So we can find 3 by 4. which is greater than 1 by 2. So therefore, 1 by 2 is not an upper bound. So in another way, any element less than 1 cannot be an upper bound. So that's what least upper bound is there. So first thing is alpha must be an upper bound of A, and any element smaller than upper bound, it cannot be an upper bound of the set. Now we can give the another definition equivalent to this. The equivalent statement for the second one is, so if you consider beta is an upper bound of A, upper bound, beta is an upper bound of A, then what is the relation between least upper bound and upper bound? Least upper bound is always less than or equal to an upper bound. So if beta is an upper bound of A, then alpha must be less than or equal to beta. Or if alpha is less than or equal to beta, if you want to say that alpha is least upper bound, any element greater than or equal to alpha, it must be an upper bound. So in this way, these two statements are equivalent. So we know that what is an upper bound and what is an least upper bound. Is it fine? Okay. So we have defined upper bound and least upper bound. Now let us define what is LUB property. So today's main talk, LUB property. So any non-empty subset of R, any non-empty subset of R which is bounded above, any non-empty subset of R which is bounded above has least upper bound. So that means any subset of R which is bounded above has least upper bound. So this property guarantees that if you show that the set is non-empty and if it is bounded above, then this property guarantees that the set has least upper bound. So there are two things here we have to observe that. The first thing is the set should be non-empty, and the second thing is the set should be bounded above. So this property is called LUB property. So we use this property directly, indirectly to proving many results in real analysis. So today I am focusing this property. So I will use this property to prove Archimedean property, and how we use this property to prove Archimedean property, and some other results I will state what are the other results we use LUB property, like that. Is it clear what is LUB property? Any non-empty subset of R which is bounded above has least upper bound. That means bounded above means what? A set is said to be bounded above. We need to at least one real number such that every element in that set must be less than or equal to alpha. That is what the set is bounded above means. So let me prove that what I said that natural numbers are not bounded above. So in natural number there is no upper bound. So when there is no upper bound, then there is no least upper bound. So the Archimedean property, this is called famous Archimedean property. Archimedean property, there are two forms. The first form is natural numbers are not bounded above. The second form I will tell you later. The first form is natural numbers are not bounded above. Here N stands for the set of all natural numbers. So natural numbers are not bounded above. So we will prove this. How this LUB property. So let us assume that natural numbers are bounded above. Natural numbers are bounded above means what? We know that natural numbers are non-empty. One is there. So therefore this set is non-empty. And we are saying that it is bounded above. So we are proving it in a contradicting manner. We are assuming that natural numbers are bounded above. That means what? There is real number alpha in R, said that every natural number is less than or equal to alpha. There is a real number such that for all natural numbers, n is less than or equal to alpha. So this means what? Alpha is we are saying that alpha is an upper bound for this. And we know that if n belongs to n plus 1 also belongs to n. If n is natural number, n plus 1 is also a natural number. So alpha, this set is non-empty. This set is non-empty, and this set is bounded above by alpha. So using least upper bound property, natural numbers has least upper bound. We are proving it in a contradictory way. We are assuming that natural numbers are bounded above. So we are assuming natural numbers are bounded above. So natural numbers are bounded above means what? I can find a real number such that for every natural number, alpha is greater than or equal to n. So natural numbers are bounded above by alpha. So by a least upper bound property, this set is non-empty and bounded above. So therefore, natural numbers has least upper. Let us say that x. So x is the least upper bound of natural number. And by the definition of upper bound, least upper bound, any element smaller than least upper bound is not an upper bound. If x is a least upper bound, then x minus 1 is not an upper bound of natural numbers. X minus 1 is not an upper bound of natural number means what? I can find a natural number n such that which is greater than, let us say that m. I can find a natural number m which is greater than x minus 2. Let me draw that. You can feel that. So what we are saying that x is the least upper bound among all natural numbers. Here 1, 2, 3, 4, etc. All natural numbers are bounded above by this x. X is the least upper bound. So now I am considering x minus 1. So this x minus 1. So this I am saying that since x is the least upper bound, x minus 1 cannot be the upper bound of the natural numbers by the definition of least upper bound. So here see that in least upper bound definition, any element smaller than least upper bound cannot be an upper bound. So using that, so here x minus 1 cannot be an upper bound. X minus 1 cannot be an upper bound means what? I need to produce one natural number here which is greater than x minus 1. That's what I am doing. So there is a natural number which is greater than this. So adding 1 on both sides, we get x which is less than m plus 1. We know that m is a natural number. M plus 1 is also natural number. So that means I am finding a natural number which is greater than x. But what is our x? X is the least upper bound of n. X is the least upper bound of n means what? Every natural number must be less than or equal to x. But here I am finding a natural number which is greater than x. These two things are contradictory. So therefore, what we have assumed natural numbers are bounded above is not true. That means what? Natural numbers are not bounded above. I hope you followed this. file is just coming. New slide is not opening. Okay, let me continue. Anyhow, so what we approved is natural numbers are not bounded above. So this is what Archimedean postulate. Next thing is the second form of natural number is before stating the second property. So we know that we measure any two things by its length depending on the distance and other units. If you consider two places, then we measure it by kilometers. If you consider the distance between two stars, we measure it by light years. And if you consider nano particles, we measure it by nano centimeters. And there is centimeters not comes, so we use the unit nano. So whatever that unit you take and whatever the distance will be there, if you go on multiplying that unit by a natural number, we can cross over that limit. So let me draw that. So suppose this is the distance y. Let me consider this is the smallest unit. Let us say that this unit is x. So unit is usually positive number. So this is the unit. If I multiply, go on multiplying 1x, 2x, 3x, 4x, 5x, 6x, 7x, 8x, 9x, million x, trillion x, I overcome this distance. So that's what the Archimedean second property. So it states that given any positive real number and any real number, there is a natural number n, so that n times x is greater than 1. So whatever the distance you give, and if you take the unit measurement, if you go on multiplying that unit by natural numbers, we can overcome those distance. We can cross that distance. So that is the beauty of this Archimedean property. So usually a student mug up that given any x greater than 0 and y in R, there is a natural number n such that nx greater than 1. So we don't look at this theorem intuitively. So this one is clear that, so whatever the distance you given, if you want to cross the distance between sun to some other galaxy star, it will be so in light years. Suppose if it is 500 light years or million light years, and if you take the light year as unit, if you go on multiplying a natural number to the light year, so we can cross the distance between two stars also. So that is what this Archimedean postulate is. So in Archimedean postulate, so it is the based on the unit. So it is based on the measurement. So in all the things, so this measurement requires, so this Archimedean postulate beautifully says that whatever the distance you give, I can overcome it. So students can also realize that every day if you go on studying, so that natural number increases and your exam tension and other things will overcome, and that knowledge what you have read every day, so it will increase your knowledge, and for the exam marks will also automatically, with the knowledge it will also that it will grade your marks more. So that's what, so consistently we need to study and focus, then only we can come over that. So we'll prove this. There is a problem in my journal. So wherever the distance is there, in that distance I'm writing. Sorry for that. It is hanging. So wherever the distance is there, in that distance only I'm managing that. Please forgive for that. Okay, let me prove that Archimedean property, second principle. Already we know that natural numbers are not bounded up. So here the second form is given any positive real number and any the distance real number y, whatever that real number y, I can find a natural number n such that nx is greater than y. Already we have proved that natural numbers are not bounded above. So natural numbers are not bounded above. So here assume that this property does not hold. That means what? Nx is less than or equal to y for all natural number n. For all natural number n, nx will be less than or equal to y. What is the property? Given any real number, positive real number and any real number y, I can find a natural number n such that nx is greater than y. So this property does not hold means what? For this x and for this y, for all natural numbers if you take, nx will be less than or equal to y. And since that x is positive, okay, so this means for all n belongs to n, n will be less than or equal to y by x. Since x is positive, so n will be less than or equal to y by x. For every natural number n is less than or equal to y by x. So this means what? Y by x, the real number, is an upper bound for natural numbers. But already we have proved that natural numbers are not bounded up. That is the first form of Archimedean property. So here, using that first property, suppose this result does not hold, that means for every natural number n, nx will be less than or equal to y. This means for every natural number n, since x is positive, n will be less than or equal to y by x. That means y by x becomes an upper bound for natural numbers. Already we know that natural numbers are not bounded up. So this Archimedean postulate we are using in many subjects in real analysis, functional analysis, directly, indirectly, sequence and series. We are using this to prove the convergence of sequence and many things. So this LUB property application is Archimedean property, and Archimedean property, from using Archimedean property we can prove many results. So density property of rational numbers. The density property of rational numbers says that between any two real number there is a rational number. If you consider any two real numbers, whatever that real numbers, if you consider 1.1 and root 2, minus root 2, whatever that, very small real numbers, if you consider there is a small gap between two real numbers also, I can find a rational numbers. So this is called density property of rational number. To prove density property of rational numbers, we use the Archimedean property. So LUB property indirectly we are using in Archimedean property. And I already told you rational numbers does not have this property. For example, if you consider this side, all rational numbers, positive rational numbers, such that whose square is greater than 0 and less than 2. I am considering a set b is equal to all positive rational numbers whose square is greater than 0 and less than 2. So for this set, so what are the elements I am considering? I am considering the elements in rational number, positive rational number, such that whose square is less than 2 and greater than 0. For example, 1 also belongs to this set because 1 square is less than 2 and greater than 0. And if you consider 1.1, 1.1 square, like that, if it is, there are infinitely many positive rational numbers are there. But among these, root 2 becomes the least upper bound of this set. And we know that root is not a rational number. So that's why rational numbers does not have this least upper bound property, and real numbers having this least upper bound property. So this is a beautiful property that real numbers have, and this is the pillar for real analysis. And so far, if you have any doubt, please ask. Any doubts? Is there any doubts in chat box? Vijay sir? If there is no doubt, and in intermediate value theorem also, I am saying that in intermediate value theorem, we know that intermediate value theorem in continuity, when you use the continuity in BSc students also learn, we know that what is intermediate value theorem. Between, in the interval, suppose f is a function from AB to R, suppose any number lies between, let us say that if x belongs to open interval a comma b, let us say that suppose xi is the element between f of a and f of b. This function is continuous function. F is a function from a b to r is continuous. Suppose there is an element xi between f of a and f of b. Let us say that. So suppose this is f of a and this is f of b. I can find a. This is f of a and this is f of b. The function is continuous. We can find an element here, say that x in AB, say that f of x is equal to xi. So this is intermediate value theorem in the continuity, and intermediate value theorem for differentiation also. I can find an element, say that whose differentiation is 0. So we are indirectly here, we are using this least upper bound property in these results. And nested interval theorem, another beautiful result in real analysis. There also we use that LUV property. And the uniqueness of, if you given any real number, there exists a unique real number such that whose power is equal to alpha. That is nth roots of real numbers. There also we use the least upper bound property to proving the uniqueness of the nth roots of real numbers. There also we use the least upper bound property. And in Cauchy sequence, which converges, we know that every convergent sequence is a Cauchy sequence, but every Cauchy sequence is not convergent. To prove that Cauchy sequence in R, which is convergent, that is what Bolzano-Weierstrass theorem. There also we use that least upper bound property. And rational numbers, we know that they are friends to us, and irrational numbers are not that much friends to us. For example, if you consider 1 by 3, we say that 0.3. If you consider root 2, we approximately say that 1.41, like that. And if you consider a circle, circumference of a circle divided by diameter of a circle, we get a constant. So it is called pi. And today is a pi day. I wish you all the mathematics people happy pi day. And we know that pi lies between 3 and 4. But there is no exact value for pi in terms of rational numbers. So, but in our high school days, we approximately say that 22/7, like that. To represent decimal representation of any positive real number, so we use the least upper bound to prove that every positive decimal form converges to a positive real number. So any positive decimal form converges to a positive real number. For example, 0.3, 0.33, 0.333. So this, if you consider this sequence, it converges to 1/3. So every positive decimal form converges to a positive real number. So if you consider pi also, so this pi and other related things in the afternoon session, Satyanarayana Reddy sir will do that. So these are the main applications of least upper bound property. If you have any doubt, please ask. Let me stop. I don't know what are the audience. If there is no question, then it for me it is very difficult to do lecturing. If you have any doubt or anything, let me stop sharing. Vinay. If you have any doubt, please you can ask.
If anyone wants to ask questions, they can ask now.
Any proof you want or anything related to real analysis, you can ask. Otherwise, because there is from 1:30 to 2:30 another session, right?
Yes. Yes.
And then let me wind up for them, take lunch and they can join that. So first, let me thank the Government Science College, the principal and all the mathematics department faculty for giving an opportunity to present a talk in this national webinar. And don't miss the afternoon session. Satyanarayana Reddy sir is a part of MTTS. My session based on Kumar sir textbook and Kumar sir video. If you want more things on LUB property and its application, it is available in, if you just type Kumar in YouTube, you can get his videos. He's an excellent teacher and he is the director of mathematics training and talent search program. If you anything you want to ask related to mathematics also, you can ask. Thank you, one and
all. Thank you, sir. I am proud to say that Chandrashekhar sir was my senior when I was studying MSc. I have discussed and learned so many things with sir while studying MSc. Thank you very much, Dr. Chandrashekhar sir, for your excellent presentation. I wanted to express my sincerest gratitude for your participation as a guest speaker at our webinar. Your contribution was invaluable and we receive numerous positive comments from attendees about your presentation. I am extremely grateful to you to touch on the subject of LUB properties and its applications in your speech. On behalf of myself and all of you, I thank you very much for your wonderful presentation, sir. Thank you.
Lastly, I want to say one thing. Whatever that, if you comes to MSc Mathematics, in BSc, okay, we'll solve only problems regarding that we state only theorem and we are by only statement, and we are not looking at what it says that. We are not going deeply that theorem what it says that. If you comes to the directly to MSc like this, then in the beginning you will find very difficult. So in the BSc itself, if you focusing on what the theorem says that, what the definition says, and if you look at some different examples, definitely the MSc Mathematics will not be difficult for you people. See here in Archimedean postulate also, it states that given any a positive real number and any real number y, there is a natural number n such that nx is greater than y. So it is the only statement. So method is the mathematical statement, but it gives lot of intuition things. That's what I in my talk I told you. Whatever that small unit you take, if you go on multiplying the natural number, it overcome those distance, those distance, whatever the distance it may be. So in life, whatever that we face lot of problems. So we lost all negative thoughts will come. If you start anybody you put some positive thoughts on you, you build on positive things, then all the difficulty will goes. So if you interpret all the theorems and other things, and if you connect it to day-to-day life, you enjoy mathematics. That is the thing I want to say, that usually if you people are whatever that you ask and other thing, and also unfortunately that my that journal is that writing instrument was struck. I am not able to start new page. So in this page, I was not able to write many things, and sorry for that. And I'm winding up because of that. And thank you one and all again for the opportunity giving me to present a talk on LUB property and its application. Thank you. Thank you, Vijay.
Thank you once again, sir. And I'm sure that your talk has really driven the audience or the listeners towards enjoying mathematics. And your very, very impressive talk on LUB has certainly given a lot of food for thought. And now I think it's time for the listeners to go for a lunch break. And with this, we come to the end of the morning session. And we're going to resume back for the third session at 1:30 exactly. So it's a request with all the participants to be back here exactly. And please adhere to the timings properly. So we'll be here back by 1:30. Thank you all.
Thank you.